Good morning, everyone. I'm Marc Zyngier. I'm with ARM. So for those who don't know me, I maintain KVM with Christopher Dahl here. Christopher's in Linaro. And for those who do know me, yes, I have cut my hair. Can we get on with it? So this presentation is the result of this exchange back in February, which made me think, do we have a technical issue or do we actually have a deep misunderstanding of what caches are, hence the KVM I'm lost in translation. So this is going to be a fairly short presentation. It's not, there's not a whole lot of slides. I want to keep it as interactive as possible. So if you have questions at any point, please interrupt me. There's a microphone in the middle of the room. And yes, it's all about caches. What does ARM offers in terms of caches? How are they built, architected? How visible are they software, or how invisible? What do we need to do with them when we do more or less nasty things? Couple of examples. Being the local Frenchman, I'm going to rant a lot. How can we get on with it? So, common misconception about ARM. This is not cache coherent. Yeah, right. This is obviously wrong. So ARM is very much a cache coherent architecture. Scales from single CPU to relatively massive SMP system. You can, almost easily find a production system with about 100 cores on it, with 2 sockets. And the funny thing is, caches can be entirely visible to software, entirely invisible to software, or any point between the two. And it is whoever actually does the implementation to decide which level of visibility software is going to have. The good news is the architecture gives us exactly the right level of abstraction to do the right thing. So why do we have these differences? Well, it all comes from the fact that the architecture gives you a way to create really, really small, power-efficient cores where you're basically not going to have a lot of gates and software is going to be a bit more involved, or something that is much larger where, you can expand another few million gates to do cache coherency in a completely transparent way. But that's fine. Gives you a way to run a VM on your smartwatch. Yes, there's some Samsung-based smartwatch with a dual Cortex S7. Yeah, you can run a VM on that. And you can run the same VM on a rather expensive piece of hardware in your data center. So the architecture is really designed to give you as much flexibility in hardware. So the architecture itself is not really innovative in any way. It's actually quite boring. You have multiple levels of caching. You can snoop across the different levels. We have separate R&D caches, no snooping between the two. It's fairly standard on the RISC system. The caches are either PIPT or non-aliasing VIPT for the D side. So that's basically the same thing as far as software is concerned. It's only for the hardware guys to sort that out. And they meet at what we call the point of unification, which is usually L2. But again, that's defined by the architecture, and you can probe that very easily. So the cache policies are controlled by attributes in the page table. So the type of the memory, whether it's normal memory or device memory, gives you things like cacheability, shareability. This is otherwise controlled by 2 enable bits, I for the instruction, C for the data, how convenient. They are not really enable bits, despite what the name says. They are more like global overrides. which means the caches are still live despite the enables being off. We're going to see that that can have some effect. They are generally invisible to software, well, to normal software. There's a few key exceptions. So how do we interact with them? Well, it's not really surprising. We have the standard thing, invalidate, clean and invalidate. We can do cache maintenance by virtual address. So it's really virtual address. I mean, you need to have an existing mapping. If you don't have the mapping for the address you're trying to invalidate, yeah, get an exception. And we have cache maintenance by setway. So is everybody familiar with what cache maintenance by setway is? No. Okay. So basically, it's really exposing the geometry of your caches. So you have a number of ways, a number of sets. And you are going really to, for example, clean one way at a time. Can be quite large. But it has a number of issues. So setway operations are local to a CPU. So if you're in a coherent system with more than one CPU, if you start invalidating locally, well, tough, you lose. You're going to break the consistency across your several CPUs. That's really bad. We don't have an all operation on the D side. We have that on the I side, not on the D side. So the only way you can do an all operation, so clean all, invalidate all, is to iterate over setways. Again, you can only do that if you only have one CPU running. Effectively, you have to restrict that to bring up and shut down a CPU. Even more fun, not all the levels have to implement setway operations. So if we go back by one slide, for example here, it's very likely that L3, which is system cache, won't implement setway operations, which means that if you do, you try to clean everything from the top towards the bottom of this schematic, you're going to flush everything up to L2, down to L3, but you won't be able to flush L3 by setway. It will just stay there. You're going to see it can be annoying. This system caches only know about VA, basically. Also, setway operations are simply impossible to virtualize. You can be scheduled out while doing a setway operation. It's just a nightmare. So if you are writing ARM code at any point in your life, and if you think of using setway operation, think twice. It's likely that what you're trying to do is the wrong thing to do, unless you're doing some really early bring up, bring down code. So think VA. So yeah, caches can be visible to software in some limited cases. If you're loading code, via your data cache or generating code with a JIT, well, you have the usual data clean, instruction invalidate, which on ARM V8 is possible directly from user space. On all the V7 cores, 32-bit basically, you need a system call for that. It's a privileged operation. You can't do it from user space. If you're doing DMA with non-cache coherent devices, it's a fairly well-known problem. In Linux, we have the DMA API for that. You do clean, invalidate, or both, depending on the direction of the transfer. More surprising, if you have a cache coherent DMA, but your caches are off. Well, you need to do the same thing because your cache coherent I/O is going to read or write from or to the caches, while your CPU is going to go directly to RAM. That could also be problematic. If you have things like conflicting memory attributes, writing to a non-cacheable mapping and trying to write from a cacheable mapping, targeting the same physical page, that's not going to work very well. And as we're going to see, it's actually a fairly common case with virtualization. So stage 2 translation. So we're definitely in virtualization land now. So stage 2 translation is basically your nested page tables, EPT on x86. Well, they give you second stage of memory attributes, and KVM always configure the RAM as cacheable at stage 2. Of course, the guest has its own page tables and memory attributes, and that gets combined into a single set of attributes that are going to be used to access whatever memory or device. So the strongest memory type wins. If you have one of the two levels that says device and the other says normal memory, it will be device. If you have conflicting attributes when it comes to cacheability, the least cacheable always wins. So if your host says, oh, this is going to be cacheable, normal memory, but your guest says non-cacheable, well, this will be non-cacheable. The hypervisor doesn't have much control over that. There's some global override, but that's really like a massive hammer for something that shouldn't require that. And yeah, it gets more complicated. So let's take a very small example of actual case we fixed a few months ago. Let's say you boot a 32-bit guest on a fairly sizable 64-bit host that has an L3 cache. And that L3 cache is a system cache. So remember, no setway operations can reach that system cache. So the 32-bit kernel is a compressed image with an embedded decompressor. It's quite funny. So you load that, you jump to it, all fine. The decompressor enables the caches, decompresses the image. Perfect. Turns the caches off and does a setway operation to make sure, oh, this is going to be in RAM. It's all fine. And then jumps to the payload. Yeah, it's bad. It's really bad. So what happens here is you've cleaned by setway. So if you see the first arrow on the right, you've cleaned by setway to L3. All good, it's there. But as your caches are off, when you're going to fetch from memory, you are going to fetch from RAM. Yeah, it's very unlikely that you are actually going to read what you've written. That's because you've flushing by setway stops really at L3 in that case. Your system caches are not capable of exposing their actual geometry. So yeah, that doesn't work. So the solution for that is to trap the setway operations and actually replace them by a VA operation that will have to iterate over the whole of the mapped memory space of the guest. So it's rather a good thing that it's done fairly early at boot time. So we don't have that many pages mapped. So it's not too bad, but yeah, it's good that it only happens at boot time. Horrible thing. Yeah?
Sorry to interrupt. So why is, considering just the decompressor that's running in the 32-bit guest,
yeah.
If you were to run that on the bare metal, would it be correct? Because
no,
it's doing
it wouldn't be correct either. It's an interesting case where the decompressor has been written for a very, very, very old version of the architecture, and where at the time where system caches simply didn't exist. And yeah, basically the 32-bit code is stuck with that. So if you want to write the decompressor to deal with VA operations, please be my guest.
But you're also accentuated here, right? Because you have a typically much larger L3 cache on a
yes.
VA service.
Yes. So if you have an embedded type system, either you don't have an L2 or an L3 cache, a system cache, or you have one that is small enough so that you don't see the problem. Yeah. In this case, we had something like an 8 meg L3, which just contains the whole guest kernel. Yeah.
So just to add to that point, the real application of the two big things, you have something like the PL310 external cache, it's probably on. So just to add to that, if you've got an external cache on a 32-bit system, it's probably going to be something like the Cortex A9 with the PL310 external cache, which will be off. And the 32-bit kernel knows how to manage that directly. But for performance reasons on newer cores, the external cache doesn't require explicit management because it responds to VA operations. But it means that it's on by default, which is where the whole problem comes from.
Yeah, thanks. So yeah, not very nice. A slightly more annoying one, which could take a lot more time to debug. So imagine you have a VM running on a rather busy host that is actually starting to swap out a lot of things. And you have a cache coherent I/O subsystem, which actually snoops into your caches. Remember, so the guest has its own memory attributes, and we never parse its page tables. It's tracy, it's time-consuming, basically. It's a lost cause. So we have no visibility on its own memory attributes. And if the guest it could start to write to memory from a non-cacheable mapping, which is not impossible if you have some bootloader, really primitive bootloader. And if we have that while that page is being swapped out via the kernel linear mapping, which is cacheable, well, things could become interesting as well. So if you look at the arrow on the left, the guest writing to some memory with its caches off, that goes to RAM, and then we evict the page via the linear mapping through the caches. Well, that's a bad idea. It's possible to just miss that write that the guest has made to memory. That could be very annoying. So we're going to write out stale data. So the way we work around that is to do a clean and invalidate each time we unmap a page from stage 2. So each time the MMU notifier calls us to say, unmap that page, we make sure that page is clean and invalidated. Again, so that the I/O subsystem will miss in the cache and read from RAM. So, yeah, this is not the expected behavior if you're familiar with an x86 system at all. Well, again, that's not completely surprising. We're not Intel. The real reason is that caches are not just here to make things faster. Yes, that's an interesting goal, but that's also how we manage the whole coherency protocol between the CPUs. If you remove the caches, the cores can't talk to each other at all. So if you use uncached memory, you are effectively bypassing all that logic, which means you have in software to reproduce it or sort of emulate it. There's really, really no magic involved. There's strict architecture rules for that. They're not necessarily easy to read, but they are there. And they are there to ensure consistency, correctness across all implementation. Whether you have fully transparent caches where basically your cache maintenance operations are effectively NOPs, to something that is a lot more, where software is a lot more involved, you issue the same sequences and it will just do the right thing. And yeah, as you said, Linux on 32-bit is not architecturally compliant. It's not very nice. There's more to virtualization than the CPU, unfortunately. There is I/O. And that's where I start ranting. So the top issue I receive over the past 3 or 4 months, maybe a bit more, is, my VGA adapter from QEMU doesn't work with KVM on ARM. That's horrible. Well, it's not completely surprising. User space uses cached memory. You do an map, you get cached memory. The guest is using an I/O remap, usually, to have access to the VGA device, which is going to be uncached. Sort of. There's a logic to that. You never read from a frame buffer, do you? Never read back from that. Makes no sense, of course. Who needs a frame buffer anyway? But it works with TCG. But TCG, for those who were in the multi-threading talk earlier, doesn't implement anything regarding caches, or basically doesn't give you an architecturally compliant version of. You can't really deal with that, so something has to be done. As it is, it cannot work on ARM. Simply not. So there's several ways to fix that. So we've had all kind of interesting solutions. One is to hack the guest attributes by forcing cacheable accesses. So that would break stuff that actually needs uncached access. And there's a number of cases where doing an uncached access is required. You could try and do some cache maintenance from user space. It's not very nice, but why not? That would require a new syscall on v7 just to do that. Not really fond of the idea. Allowing user space to do an uncached mmap. Okay, but what if the guest maps it as cached? We have the opposite problem. We're not fixing it. Trapping every possible access. Yeah, that will work. That will work. Not very quickly. The only real solution is to actually tell the guest that whatever device we put there is cache coherent, because that's really what it is. So far, we are lying to the guest. We're saying, yeah, this is a VGA card. It's a device. Don't worry about it. We're really lying to it, and we're relying on certain properties of a different architecture that really don't apply here. I mean, you can turn it upside down if you want. That fact won't change. So how did we end up here? So VGA was invented in 87. Who was born in 87? Yeah, not that many. Yeah, my personal joke is you wouldn't plug a PDP-11 DSA controller on a Xeon, would you? Okay. So why put a VGA card, an emulation of a VGA card on an ARM system, which is completely alien to the architecture? Also, the ARM VMs have absolutely no legacy at all. I mean, the oldest ARM VM in production is probably 5 months old, not more than that. And I run it. So there's really, really, really no legacy at all. So why do we have to introduce that legacy? We don't even have a standard platform. We don't even need one. I understand that for an x86, it's fairly standard. There's a number of well-known peripherals sitting at well-known addresses in the memory map. We don't have that requirement on ARM at all. And we use para-virtualized devices for most things. The console, the real one, the serial one. We have that for networking, for storage. And now we have virtio VGA. And to me, it looks absolutely awesome. This is what we need. We can make sure it doesn't have any form of legacy. And we don't have to lie about the fact that it's a virtual device. It's part of the name. So now let's look at it. Who plugged that thing on my beautiful VM? KVM doesn't care about any form of emulated devices, really, apart from things that are directly in the kernel. User space, whether it's QEMU or KVM tool, they just do what they're told. So where's that coming from? Well, it's very likely that high-level tools are completely oblivious of architectural differences. And if all you have is Libvirt, absolutely everything looks like an x86. That's a bit annoying. So I would hope that someone that is familiar with Libvirt or whatever's on top of it, which I'd rather know, will add some form of per architecture profile. Shouldn't be a big deal. We shouldn't have to, have an ARM VM that is basically a copy-paste of an x86 VM with just, let's remove the x86 CPU and drop an ARM there. Can't really work like that. So back to coherency, really. We have different requirements, really, for emulated and physical devices. You can't really manage them the same way. They really have different requirements. So it's likely that firmware has a role to play in exposing the differences between the various devices. And especially on ARM, there's a general need for topology information. And we have that on bare metal. We really have to describe how things are interconnected and how coherent they are. And there's no reason why VMs should be an exception. So when we have device tree, we have ways to specify the level of coherency. So for PCI, this is done on a per root complex basis. So if you have two different set of devices, some coherent, likely to be emulated, and some non-coherent, likely to be physical, it means you may have to expose them as two different root complexes. Shouldn't be a big deal. QEMU has enough code to deal with that. When it comes to a CPI, there's also attributes to expose that. So CCA, which is mostly supported on x86, but now has also getting some ARM support. And there's the whole IORT framework, which is really extensively describes the ARM diversity when it comes to coherency and the way request to IDs, stream IDs, all that is transformed. So it's not ideal. It's maybe not fine-grained enough. At the root complex level, it's a bit big, but it's a lot better than the current status quo we have. So, as a conclusion, yeah, KVM is really heavily x86 oriented. Not really surprising. Nobody would doubt that. Trouble is, not all the solutions that worked on x86 make sense on ARM. We end up with with Franken VMs built with bits of foreign architectures globbed together. We have the chance of a clean slate, and I really wish we start with that. So it doesn't take much effort to fix KVM. The architectural issues I've outlined, they take a bit of effort to fix, but once you get the gist of the problem, you can go and look wherever we could do something slightly scary. And everything's documented. I really recommend reading the ARM, so the ARM Architecture Reference Manual. If you have trouble sleeping, it's really, really good. It's amazing. And it's growing. There's additional reading material and all that. The joke carries on. And we have, irrespective of the architecture, we have really, really efficient solutions to deal with virtualization. Para-virtualization is really good, really efficient. The talk that's taking place just now at the same time is about virtio VGA, so you should go, really. And the real problem seems to be in firmware, because firmware seems to have grown out of x86 as well. UEFI is extremely x86-centric, and hopefully there are ways to retrofit some para-virtualization support into it. And the high-level tools, where, Libvirt, seem to completely ignore any other architecture. So that shouldn't be hard to fix. But as a general trend, I wish people wouldn't assume that x86 is always the model to follow. There's a lot of good things being done on the x86 side that don't necessarily always apply to what ARM does or other architecture do. Thank you. Questions? Yes.
I'm working at Red Hat, and I'd just like to say that Libvirt recently does actually really support ARM very well, and tools like virt install.
So
the problem may be if you're using something like Ubuntu, you're probably using a really, really, really old version of Libvirt or virtinstall, and they probably don't have all the changes. But we do have a developer who works full-time on getting ARM to work with virtinstall.
Not Libvirt, it's QEMU. It's whatever QEMU does to send the VGA adapter to VM. Libvirt knows that it's an ARM VM, sure.
But I mean, for example, if you use virtinstall to create an ARM guest, it won't add a VGA adapter because it knows that makes no sense, and all that stuff does.
Okay, I stand corrected on that front then. Thank you.
I think the gist of this talk is that whichever way you use to instantiate a VGA controller, the only thing QEMU can do now will break. Right,
so if you ask QEMU to instantiate an actual, a proper VGA controller, that is doomed. Not necessarily because of QEMU, but because there's all kind of strings attached that come to that. The kernel knows that a VGA card is a device, so I can map it uncached, and that will work. And that on the KVM side, that completely relies on the fact that on x86, writing to an uncached mapping is going to invalidate the cached mapping on the other side.
So why doesn't the guest adhere to the cache principle?
Because we have a lot of legacy there in both the kernel and EFI. We assume that a driver written for an architecture, because it compiles for another one, is just going to work. This is not the case.
Then fixing the VGA driver in the guest is another alternative.
It's an alternative. Do we really want to go there? It requires now to parse attributes. Is this device coherent or not? There's a number of really, really annoying details to get right across all architectures. And in the end, something that is not going to be really efficient. The point I'm trying to make here is, do we really need to go through all that trouble? I mean, for the sake of it, fixing it would be good, I agree. But do we really want to do that? Why don't we use something that will be really efficient and matches the clean state we have?
Yeah, so on that should be fixed the driver thing, it actually comes back to the virtio VGA, which is definitely great way to go, but you don't have control over the install media for all guest types you want to boot. And so you can't have virtio VGA in there or a fixed driver necessarily in that guest type from the get-go. And so you really have to have this emulation fallback, at least for installation, before you have a chance to install virtio VGA.
I have two answers to that. One, I don't really buy but you have an pre-existing guest. We don't have that many existing guests on ARM. Really, realistically. Yeah, if you deliver an install media onto my desk, I will retract that statement immediately. But
the guest type I was referring to is more local to Seattle.
So the other thing is, for me, if you're talking install media, and assuming that that problem, you could also install using a serial console. I don't. That the frame buffer I always find the frame buffer especially for a server, that sounds really, really scary. I mean, I'm a big fan of something that I can actually log and inspect later. But yeah, I take your point.
And one other thing was reference to slide number 2. So can you give an example of where the guest cache attributes, being more strict, overriding the second stage 2 page table attributes is a good idea and useful?
Well, device pass-through is one reason. You don't really have to assume what kind of coherency the host is going to put there. It doesn't really always know. You may want to serialize things in RAM for other reasons. You can, if you have a non-cache coherent device that is going to read directly from memory, and you don't want, take for example, a bootloader. A bootloader doesn't necessarily need to enable the caches, set up page table for that. It's cumbersome, it's complicated, and they are lazy. So they're going to say, okay, this device is not cache coherent anyway. I'm going to just read from memory, and it will all be good. I'm not going to bother with cache maintenance operations. If you enforce cacheability at stage 2, so you override the guest attributes, which are default non-cacheable, all of a sudden you will have the guest will read from its cache, not necessarily from RAM, and you may simply read stale data. So you break existing code with that. So it's really important to, in that kind of situation, I mean, it's never perfect. You will always find corner cases where one thing break. But forcing, allowing the hypervisor to enforce cache attributes always, it's not necessarily a good idea. You can always find cases where that breaks.
I would just observe that the lifetime of virtual machines significantly exceeds the lifetime of a given hardware generation, whether you like it or not.
I do like it.
And it seems like the guest needs to be aware of the hardware topology.
No, not necessarily.
It needs to be aware of the cache topology, which is already described by the architecture.
Right. So, for example, I install a NIC and I pass it through because that's the best way to get network performance today. And then I want to switch to a software-backed emulation of this NIC. Does the guest need to be in on the joke?
No, the guest doesn't need to know anything about that. He shouldn't need to know about that. As long as you keep the same level of coherency. If you change the level of coherency between the two, that could become a problem. But you are effectively changing the hardware, whether it's a virtual hardware or physical hardware. You are effectively changing the properties of the hardware. So migrating VMs on different hardware works as long as they have the same properties. You can't, I mean, it would be like, okay, I'm switching the type of bus. That wouldn't work either. If you change the level of coherency between your physical device and your emulated device, you break, but you will break on any architecture as well.
Right. Thank you.
Again, we're ignoring the fact that we're telling the guest that it's a coherent device, and then the guest says, man, I'm not going to expect that. So, kind of crazy to expect that to work.
Hi, name's Laszlo, and I work on a guest UEFI firmware for Red Hat. And first, I'd like to ask how much time we have left, because my comments could be longer a bit. 5 minutes? All right, I'll just do it quick.
Otherwise, Common Simulator.
Yeah. So can you jump to the last slide? Oh, this is the last slide, the penultimate slide? Okay. So I tried to count the recommendations or suggestions you made about possible ways to fix this problem. And so I think number 3 is here to fix KVM. I think that means making QEMU smarter about all that stuff and set up the mappings correctly.
So QEMU doesn't have any say in that, really. What QEMU can do is to expose some firmware-related information, at least to say, this is coherent. Don't bother doing anything else.
That's an earlier. Okay, just can you go back to one of the
So there was,
slides?
I had a slide for that, blah, blah, this one.
Yeah, exactly. So what we do now in the firmware is okay. Let me get back to the firmware interface where all this comes from. Yeah. So in UEFI, when you have a video card abstraction, basically it's a graphics output protocol, and it has various methods to write to the screen, and one of them is blit, and it would be possible to back the blit method with a virtio VGA capable implementation, so that it actually speaks virtio, and then all the memory barriers would be inserted in the virtio protocol itself. So that would be one solution. The problem with that is that once you leave the firmware and hand off to the runtime OS, the protocol becomes unavailable, and the runtime OS is supposed to use the frame buffer it inherits directly, so poke into the frame buffer directly. And so it wouldn't talk virtio until you installed the smart runtime OS guest driver. It could only use, word size access or something like that. And so you could either remove the complete memory slot backing, and then each access would trap, but it would be horribly slow, or else you could advise the firmware to make it realize that it's actually a coherent device, and it shouldn't set up an uncached mapping for that in the firmware.
Yeah, so that's
I think that's the most portable and best solution. Like, just tell the guest the device is coherent, and if because QEMU now generates a DT for the firmware to parse to know where the MMI ranges are, and if you I don't exactly know how the root complexes are represented in the DT, but if the devices can be grouped into two separate root complexes and say that these are coherent, these are non-coherent.
Yeah, that's the idea.
That that's perfectly. It can be handled very well.
So that's one of the recommendations. Describe your coherency attributes. The other thing is, why can't we support virtio VGA really early on in your operating system? There's, is there. Okay, it's fairly recent, just got merged, but hey, we like to live on the bleeding edge anyway.
Well, UEFI internals are, so they kind of make it heavy or hard to use virtio. Virtio is, it depends on a lot of stuff that's not available in the very early phases of UEFI. But with virtio VGA, it's true the real problem with that is that it wouldn't allow the runtime OS to just inherit the frame buffer set up by the firmware and just poke into that until a smarter driver comes along. And
no, it needs to be the driver.
Yeah. So I think if I can make if I can express my preference here, I think for QEMU the best or most portable way forward would be to just generate a smart DT and explain the guest firmware what is supposed to be mapped as cached versus device memory or uncached. Because right now, it does work, I think, even with KVM, what we have, but it's a hack. It's a static hack that we just say, although we should really map this as device memory because it's a VGA card, we know that it doesn't work due to the way that on ARM, the caching attributes are combined between S2 and S1. So if that could be made dynamic and the host, the QEMU, DT generator could advise.
I'm all for that. I mean, I don't mind whichever solution you want to use.
All right.
All I'm saying is tell the truth to the guest.
Yeah,
don't
absolutely.
lie to it.
Absolutely. So what I see the problem here is that just the guest lacks sufficient dynamic information. So for me, that's all. Thank you.
All right. Thank you. Thank you very much.